Hi, Assalamualaikum. So the next subtopic we are going to learn is 11.2 Young's Modulus. There are a few learning outcomes here. First is to define Young's Modulus. Second is to discuss strain energy from force elongation graph. Third one, to discuss strain energy per unit volume from the stress strain graph. And last one is to solve problems related to Young's modulus. Okay, let's look at the first one here, the definition of the Young's modulus. So it is the ratio of the tensile stress to the tensile strain if the proportionality limit has not been exceeded. Ataupun kita boleh keluarkan formula di mana Young's modulus adalah stress divided by strain, since dia cakap dia adalah ratio. So stress divided by strain. So dekat sini kamu kena ingat setiap material akan ada value Young's modulus sendiri. So aluminium, copper, what else, steel, they all have their own value for Young's modulus. So Young's modulus ni lebih senang mau cakap dekat sini, dia adalah indicator of how easily the material is bended or stretched, ataupun dia adalah indicator the stiffness for the material. So semakin tinggi value Young's modulus, semakin tinggi the stiffness of the material. Okay, so since the Young's modulus is equal to stress divided by strain, each of these value has its own formula, di mana stress adalah force divided by the cross-sectional area, and strain adalah the elongation divided by the original length. So apabila kita susun, kita akan dapat Young's modulus is equal to FL0 divided by AE. Okay, so kita akan gunakan formula ni untuk cari Young's modulus. So Young's modulus is a scalar quantity, and the unit for the Young's modulus is kg meter per second square, Newton per meter, or Pascal. But usually we are given the value in terms of Pascal. Okay, selalunya lah dalam soalan kita gunakan unit Pascal. Okay, tetapi kalau menggunakan these two unit pun boleh. Okay, so since I said that Young's modulus is to indicate the stiffness of the material, so it does not depend to the length of the wire. Okay, tidak kisahlah wire tu lebih panjang atau lebih pendek. Okay, dia tidak mempengaruhi the Young's modulus. So this Young's modulus depends on the material of the wire. Okay, so boleh tengok dekat dalam table ni, untuk aluminium, bond, brass, copper and steel, they all have their own Young's modulus value. So from here you can see that steel has the highest Young's modulus, and then the lowest Young's modulus value is for bond. So dekat sini kita boleh cakap lah steel is stiffer than all of this material, and the less stiff here is the bond because it has lowest value for Young's modulus. Okay, last one, we look at the relationship between force constant and Young's modulus. So kita boleh gunakan formula ni, di mana force constant is K is equal to Young's modulus times width area divided by the elongation, not the elongation, the original length of the wire or the material. Okay, daripada mana kita dapatkan K ni? So K here is actually from the Hooke's law, di mana Hooke's law adalah sama dengan Kx, and X here is the elongation. So kita boleh tulislah F adalah sama dengan Ke. Okay, so let me show you real quick the derivation here. Okay, kita tahu Young's modulus adalah sama dengan FL0 divided by AE. This one right here. So F dekat sini adalah sama dengan KE. Okay, the force constant times with E. So, apabila kita masukkan Young's modulus, this one KE, L0 AE, and then these two we can cancel out and then rearrange, kita akan dapat K sama dengan Young's modulus times with B area divided by L0. That's why kita dapat this formula. Okay, next one we look at strength energy. Okay, let's consider a wire here. So this is a wire connected with an object with mass, let's say 2 kg. So this wire is connected with an object. So this object has a mass. So meaning that this wire is being pulled downward by a force, where the force is known as weight force. So apabila wire ni ditarik ke bawah, this wire will stretch. Okay, the wire will stretch, meaning that there is a work done on the wire. Okay, work is done on the wire. When work is done on the wire, this wire actually store energy. So the energy stored here, we call it as strength energy or elastic potential energy. Okay, so let's consider we have the force against extension graph. So force F and then extension E. Okay, extension E. So as you can see here, the graph is linear graph, meaning that when force increase, extension pun increase, as long as it doesn't exceed the proportionality limit. Maksudnya dia obeys Hooke's law. Okay, apa maksud proportionality limit dekat sini? Maksudnya apabila kita stretch wire tu, dia boleh kembali ke bentuk asal. Okay, so from the graph here, okay, of the force against extension, the area under the graph here is actually equal to the work done, which is also equal to the energy, because we learned before that work done is a transfer of energy. So benda yang sama lah. So here, in order to find the work done, we are going to use this formula here, di mana energy adalah sama dengan 1/2 times with F times with E, elongation. Okay, so since we want it to be within the proportionality limit, meaning that dia obeys Hooke's law, force di sini adalah sama dengan Kx, di mana K adalah the force constant, and then X here actually the extension. So we can say that energy is equal to half Ke and then E. So kita boleh cakap lah U is equal to half Ke square. X dekat sini extension. This one kita gunakan untuk spring sebelum ni. So untuk chapter 11 kita akan gunakan E, di mana kita gunakan extension. Okay, next one, let's look at the strength energy per unit volume. Okay, when we have a material, a wire, so let's say this is a wire, okay, with area, a certain area and a certain length. Okay, apabila wire ni dia stretch, maksudnya, okay, let's say original value dia adalah 1 meter. And then kita akan stretch, so dia akan stretch macam ni lah. Maybe this is like what 0.2 meter. Okay, apabila wire ni dia stretch, yang berubah bukan sekadar length sahaja. Actually the whole volume of the wire, area ni akan berubah, the length of the wire also berubah. Maksudnya volume of the wire will change. So when the volume also change, the energy stored, okay, within the material we call it as the energy per unit volume, U divided by V, di mana volume dekat sini adalah sama dengan area times with the original length. This one here. Basically, this whole thing is the derivation. Actually, you don't need to know. Kamu just kena ingat the formula untuk strength energy per unit volume is this one here. Okay, di mana this one adalah stress, this one adalah strength. So, apabila kita plotkan graph of stress against strength, kita akan dapat satu linear graph. Maksudnya kalau stress tinggi, strength pun akan tinggi. Dan area under the graph here is equal to the strength energy per unit volume.